So where were we? We were talking about this problem. What is the sum of the reciprocals of the perfect squares? And we saw that it was solved by Euler, who proved that this infinite sum is actually equal to pi squared over 6, 90 years later. So this was in 1735. Okay? Now, the method he used was actually kind of brilliant because it allowed him to solve many other problems at the same time. So his method generalized. Okay? In order to prove that the sum of the reciprocals of all the even powers is equal to something that looks like this, a power of pi times some rational number. Okay, so his method generalized, and it allowed him to find that the sum of the reciprocals of the fourth powers, let's say, okay, is also in this form. It's actually equal to pi to the fourth over 90. Okay, and of course the sum of the reciprocals of the sixth powers, same thing happens there. Okay. That one's equal to pi to the sixth over 945. And in general, every even power was solved, and they all take this form. Okay? Surprisingly enough, pi comes in there. What else did Euler's method allow him to conclude? So Euler proved, let me just write down what he proved here. The first thing he proved is that the sum, I'm going to use summation notation, n equals 1 to infinity of 1 over n to the 2k is equal to pi to the 2k times rational, so times p over q, pq in the natural numbers. Okay, that's what he proved. His method also gave him the alternating odd series. So he found that the sum from n equals 0 now to infinity, negative 1 to the n over n to the 2k plus 1 can also be written in this form. It's also p over q, I'm going to write a over b this time, times pi to the 2k plus 1. Okay? So let's do an example here, because the summation notation is always confusing. If k equals 0 here, then you get 1 over 1 minus a third plus a fifth minus a seventh. Okay? Just the powers of 1, odd powers, odd numbers only, and alternating. So plus minus, plus minus. This one turns out to be equal to pi over 4. Okay? And the next one, when you cube all the numbers like this was also solved by Euler, and it turns out that that's equal to pi cubed over 32. Okay? And all the series have that same form. Okay? So Euler solved all of these problems in one shot, and also all of these problems in another shot. Okay? So he took this one open question that nobody could solve for 90 years, and then in the same method which solved this problem, he solved all these other problems as well. Okay? Totally awesome. But he didn't solve several things, so some things are still open here. Knowing that all the even power sums take this form, the natural question is, what about the odd power sums? What if we make the exponent 3, the sum of the reciprocals of the cubes? What is that going to be? What about the fifth powers, and so on? So that's actually still an open problem. Open problem. What is the value of 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, and so on? Okay? So since that time, no one was able to solve this problem. Okay? No one could find an expression for this. A natural guess would be maybe pi cubed times some fraction. But it turns out that if that's the case, then the fraction has to be very, very large. Okay? So chances are that that's not correct. Okay? Euler himself conjectured something about the form of this, having a pi and also a log 2 term in there, times maybe some fractions. We still don't know if that's correct or not. Okay? So what is the value of this? That's an open problem. And all odd powers. Okay? All of those are open problems. Maybe I should write on the next board over here. So the first series that you see there, okay, the sum from n equals 1 to infinity of 1 over n to some power, okay, that is a function if you allow the power to be the variable, and it's called the zeta function. zeta function. Same zeta function that the Riemann hypothesis is concerned with, but we're not going to talk about that today. It's too hard. Okay? So the zeta function, it's a function of s. I can't draw a zeta, so I'm just going to write z of s. Is defined to be the sum of the reciprocals of the s powers. Okay? So we know what zeta of 2k is for an integer k. The open problem is what is zeta of 2k plus 1. Okay? So the open problem here is what is zeta 2k plus 1. Okay? Another open problem stemming from this result. Okay? Here we don't know the odd power cases. Here we know the odd power cases, but we don't know the even power cases. Okay, so that function with the alternating odd powers is called the beta function. Okay, beta function. And the b in the beta is a beta. Beta function, written like this, beta of s equals the sum from n equals 0 to infinity, negative 1 to the n, over 2 to the n plus 1. So this just generates the alternating odd numbers, and the exponent here is s. Okay? Beta function, zeta function. So another open problem is, what is beta of 2k? Okay? Where k is an integer. We know beta 2k plus 1. We know the form that it takes. We have a formula for the answer in general. We don't know what the even power case is. So in particular, we don't know something like this. 1 over 1 squared minus a third squared plus a fifth squared minus a seventh squared, and so on. Okay? This is called Kaplan's constant. Actually, it's denoted G. I don't know why. Kaplan constant. Okay? There we go. Another unsolved problem. Now, there are representations for this series and this series in terms of other series which maybe converge faster so we can compute the decimals in terms of integrals and other things. But no one can find a closed form. So that's the open problem here. There are some results available. This, for instance, this value of zeta 3 has actually been proved to be irrational. Proved irrational. Okay? Not really a surprise, but proving that a number is irrational could be difficult. Okay, this was proved to be irrational by a guy named pi+e in 1978. Okay, he proved that result. This is not known whether that's rational or irrational. Okay, not known irrational. So there's actually a good chance that since nobody is able to solve these problems, that perhaps these two sums, the ones with the even exponents here and the odd exponents here, zeta 2k plus 1, beta 2k, perhaps those sums are just random numbers which can't be represented at all in terms of known constants like pi or e. Or perhaps there is another fundamental constant that they can be represented in terms of, but we just don't know what that constant is. It hasn't come up anywhere else. Okay? So those are two possibilities. All right, so that's that. What else is known? Very little about these series. Okay, so pi+e proved that this was irrational. He did not prove that the powers of 5 were irrational, or zeta 5. There is another result that infinitely many of the zeta odd are irrational. That was also proven quite recently in the 20th century. And then someone else proved that actually one of zeta 5, zeta 7, zeta 9, or zeta 11, one of those has to be odd. But he didn't specify, or irrational, sorry. But he didn't specify which one it is. Okay? There's a little bit of progress that's been made, but very, very little. Okay? This is still largely an open question. All right, so let's move on. That's a little bit of analysis, a little bit on finding what sums equal to. Okay? It turns out that the problem of finding values of infinite series is very difficult and subtle. So here's one example. Okay, so here's a couple more open problems. I think they're open. problems. If you change something, a little thing about an infinite series, you can change a very easy problem into a very hard one. Okay, so here's an example. Okay, we all know what this adds up to. The sum from n equals 1 to infinity of 1 over 2 to the n. Right? This is 1 over 2 plus 1 over 2 squared. So a half plus a quarter plus an eighth. Right? That adds up to 1. Right? You take half of something, then you take half of that half, another half of that half, so on. Okay, this infinite sum adds up to 1. This is the geometric series. Okay? Geometric series. And it's quite easy to prove that that adds up to 1. In fact, any powers of n you have, it's pretty straightforward to find the value of the sum. However, do that. Subtract 1 from the denominators. All of a sudden, we have a problem. This turns out to be quite difficult. Now, I don't quite know if it's open. Okay, so I'm going to say this is maybe open problems. Okay, because I'm not sure. I'm not able to compute the sum, and I've never seen it computed anywhere. So my guess is that this is just an unknown thing. Okay, whether this thing, we know that it sums up to something, but we don't know what it equals. Okay, same thing with something like this. It's fairly straightforward to determine, let's start at 0 this time, the sum of the reciprocals of the factorials. It turns out that they add up to e. If you haven't seen that yet, you'll see it at the end of the year when you talk about Taylor series. Again, plus minus 1, or anything else. I just wrote 1. You could have added 10 or 15 or whatever. All of these turn out to be unknown, or at least I have never seen them. So if they are known, they're probably difficult. Okay, so that's why I put that maybe in. These are maybe open problems. You guys can check that yourselves if you want. Okay, I tried Googling it, but couldn't find anything. Okay. All right, so it turns out that if you change the series very slightly, you might turn an easy problem. Both of these are relatively easy. They're certainly easier than those other problems that I've been talking about than this. Okay, but if you change the series ever so slightly, all of a sudden, you might not know what the series adds up to. Okay? It turns out, actually, that there are even series that we don't know if they converge or not. That's probably a little more surprising because obviously for finding what the value of convergence is, what the value that a series converges to, that's pretty obvious that that might be difficult. And that if you come up with some really strange example, you just have yourself an open problem. You could generate many open problems in that same way. But finding a series whose convergence is unknown, that is, you'd think that perhaps we just know maybe all the rules that we have for testing convergence, as long as we apply them enough times or in the right way, they would be able to tell us the convergence of any series at all. But it turns out that that's not the case. There are some series for which convergence is not known. Here's a famous example. So open problem, I guess that was number 1. This would be number 3. Okay. So a series whose convergence is not known. It is not known. This is called the Flint Hills series. And it looks like this. You're summing over all the integers, n equals 1 to infinity, and the terms look like n cubed sine squared n. Okay? We do not know if that beast converges. Okay? So we're not even asking about the sum yet. We don't even know if this sums up to anything. Okay? Perhaps the terms just perhaps the thing just goes off to infinity. Now, why is this problem hard? Because the sine squared in the denominator causes problems, right? Sine of pi is 0, and sine of any multiple of pi is 0, okay? Now, if you plug in natural numbers n, we're never going to get a multiple of pi coming up in the denominator because pi is not rational. But we can get numbers that are very, very close to pi, like sine of 3, for instance. 3 is pretty close to pi, so sine of 3 is going to be pretty close to 0. And when you sub in 3 into this series, you get 1 over 3 cubed, so 1 over 27, times something small, so perhaps that'll be something less than 1 when you actually do that multiplication. Perhaps, I don't know if it is. But then you're going to have 1 over something which is maybe less than 1. That's going to be something more than 1. Every now and then in this series, you might have a larger term, okay? Maybe not something that's of the size of 10 or 20 or whatever, but you might have something that's close enough to 1 or close enough to a harmonic term, perhaps close enough to 1 over n, such that actually when you take the whole series and try to add it up, we diverge. We go off to infinity, okay? If you remember, the sum of 1 over n from n equals 1 to infinity diverges. Okay? Again, if you haven't seen this yet, then you're going to see it next semester in Cal class. Okay? So that series diverges. So as long as not too many terms of this series look like this, then we're okay. But if too many of these terms look like these harmonic terms, if the n cubed and the sine squared n sort of multiply together and the exponents maybe here, sine squared n could be something pretty close to 0 for large n, so perhaps something of the order of 1 over n squared. Then if you multiply these out, you'll get something of the order of 1 over n here in this series. And you'll get a harmonic term every now and then, which means that this series would diverge. Okay? So it's not known whether that series converges or not. Okay? And again, the problem is with the sign and how well you can approximate pi using natural numbers. Okay? So problem here is, here lies in the following. We don't know how well, I'm going to put the well in quotes, how well pi can be approximated using natural numbers. Okay? If it turns out that pi can be approximated very well, sorry, not naturals, rationals rather, okay? Because we're looking for sine of a natural being very, very close to a natural times pi. So if you divide that natural out, you get a fraction being very close to pi, okay? We don't know how well pi can be approximated using rationals. And again, the well is in quotes because there's a mathematical way to formulate this question. We don't have enough time to go into it. But that's what the problem can be transformed into. A question about how well you can approximate this irrational number with rationals. If it turns out you can approximate pi too well, meaning that you can find small enough fractions that agree with pi to many, many decimals, then the thing will diverge. If you can prove that that's not possible, if in order to get a good rational representation of pi, it's necessary to make the numerator and the denominator of your rational very large, then it turns out that this is going to converge. Okay? And of course, the value it converges to is unknown. Why would it be known? All right. There's actually even simpler things which we don't know the convergence of. A sequence, for instance. Okay, so this was a series. There are actually even sequences that we don't know convergence. Okay? So here's an example. xn, where the nth term is 1 over n squared sine n. Okay? So looking a lot like this, except the exponents have been modified, we don't know whether that sequence converges. It's unknown whether this converges. Okay? It's known that if it converges to 0. Okay? But again, the problem of convergence can be translated into how well you can approximate pi. Right? And the approximation of pi question is still an open question, and so this is still an open question. Right? Okay, let's move on to something easier. So this is probably the hardest stuff that we'll talk about. I apologize if you didn't understand completely everything. Simpler open problems that are out there. Rationality and irrationality in general. So forget about approximating irrational numbers using rationals. That might be a very, very hard question. But it's not even known whether certain numbers are rational or irrational. So numbers like pi and e, okay? So I guess this would be topic 3, I suppose. Analysis. This would be algebra, I guess. Okay? Open problems from algebra. Here's an open problem. So we know that numbers like pi and e are irrational. We know pi and e are irrational. Actually, they're transcendental. Transcendental. This is a hard word to spell for a mathematician. Transcendental, actually. Okay? But if we start mixing pi and e together, all of a sudden we get a bunch of numbers which we don't know whether they're rational or not. So here are some open problems. Open. Is pi plus e rational? That, believe it or not, is an open problem. It seems like, well, of course it's irrational. We choose two irrational numbers which have nothing to do with each other. We add them together. Why would we expect a rational? But nobody knows how to prove that. Same thing with other things. Is pi plus e rational? Is pi minus e rational? Is pi times e rational? Is pi divided by e rational? Is pi to the exponent e rational? Or pi to the exponent pi? Or e to the exponent e? All of these we don't know. Okay? Are they rational? Open question. Okay? Curiously enough, e to the pi actually has been proven to be irrational. Okay? Transcendental energy is irrational. Okay? All right, any progress that's been made on proving that numbers are irrational or rational or transcendental? Yes, we know that all square roots or cube roots or fourth roots or anything like that of an integer or any other, well, it could be a rational number, but any integer which isn't a perfect square or a perfect cube, we know that all those numbers are irrational. That's pretty straightforward to prove, and it's been known since antiquities, the Greeks. Okay? So progress, not specifically maybe about these problems, but more about rational, irrational in general, okay? On proving irrationality. Okay? What do we know? The kth root of n is irrational if n is not power of k. Okay? So something like the square root of 2 or the square root of 3, or the cube root of 2 or the cube root of 3. Okay? Or the cube root of 4. All of those are irrational. Okay? So here's a way to generate a lot of irrational numbers. Of course, any rational times any irrational is irrational. So from pi and e, knowing that those are irrational alone, we can generate a lot of other irrational numbers. Okay? What else do we know? I'm going to put this on a separate board because it's an interesting enough result. We know that, erase this stuff here. We know that if we raise a rational number to the power of an irrational number, we get an irrational number. Okay? Actually, the result is stronger than that. Okay? If we have alpha algebraic, okay, beta irrational algebraic. So what algebraic means is not transcendental, or the solution to a polynomial equation solves a polynomial equation. Like root 2, for example, is algebraic because it solves x squared minus 2 equals 0. Okay? That solves a polynomial equation. If alpha is algebraic and beta is irrational algebraic, because obviously alpha being algebraic, that takes into account all integers and things like that. Beta is irrational algebraic, then alpha to the beta is transcendental. Okay? So that's actually a pretty deep result. Difficult to prove. 1934, I think it was. It was proved by two guys, Gelfand and Schneider. So now it's called the Gelfand-Schneider theorem. Or the Gelfand-Schneider theorem. I don't know how to pronounce that. But there's that theorem. Okay? So there's a little bit of progress that's been made. So this theorem allows us to conclude that something like 2 to the power root 2 is transcendental. Okay? This is algebraic. That's also algebraic and irrational. Both of these numbers solve polynomial equations. 2 solves the linear equation x minus 2, and root 2 solves the quadratic equation x squared minus 2 equals 0. Okay? But still, this theorem doesn't tell us anything about what happens when you have a transcendental and you raise it to another transcendental, or what happens when you add 2 transcendentals together and multiply them. Okay? So, what other problems can we come up with the numbers pi and e? Okay, so here are some problems with them being rational or irrational. Here's another problem that you can come up with, which is actually, it seems kind of silly. It seems like we should really know this, but it turns out that we don't. We could look at the decimal expansion of pi and ask about it. We can ask something like, well, we know that pi is irrational, so that decimals go on forever without repeating and without terminating. Okay? How many times does the digit 7 appear in the decimal expansion of pi? Okay? That is an open problem. Open problem. Okay? How many times does 7 appear in the decimal expansion of pi? It seems like, of course, it should be infinitely many times, right? But no one knows how to prove that. In fact, a bit more should be true. We should expect the 7 to appear roughly a tenth of the time. Okay? But again, turns out to be a very difficult question. And for most numbers that you pick, this question is very difficult. Like we can change pi to e now and ask, where's pi? There we go. You can change that to e and ask the same question about e, or root 2, or probably any other number, okay? As long as we don't have a number which, you know, we know that certain terms here are specifically excluded, okay? So this gives a good opportunity to introduce normal numbers. Normal numbers, and then we'll talk about progress that's been made here. Okay? A normal number is a number where all the possible decimals that are in there occur sort of equally likely, with equal frequency, or the expected frequency. Okay? And number n, let's not call it n, let's call it x, because we know that we're going to have an irrational number here. We want a decimal which goes on forever, which does not terminate or repeat. Okay? And number x, I guess not in Q, okay, is normal if any k string of digits, of decimal digits, so say we're working in base 10 here, decimal digits, occurs with frequency, occurs with probability rather, 1 over 10 to the k. All right? So let's explain that definition. If you set k equal to 1, then if we have a normal number, we have each of its decimal digits occurring with equal probability. Probability 1/10. Okay? A 1 occurs a tenth of the time, a 7 occurs a tenth of the time. If we set k equal to 2, what we're saying is that a string of 2, 3 occurs 1/100th of the time. Okay? 5, 6 also occurs 100th of the time, or 7, 2. Okay? Same thing for 3 decimal strings and so on. All right? So basically, a number is normal if its decimals are randomized enough that we have exactly the expected frequency. Okay? So those are normal numbers. And here's an open problem associated with normal numbers. Okay? Open problem. Prove that almost any number is normal. We don't know how to do that. Okay? Actually, something stronger can be said. Exhibit an example of a normal number. So find an example of a normal number. And prove that it is normal. Okay? That comes with it. So find an example of a normal number. Of course, we hypothesize that things like pi or e are normal, but we can't prove that. Also, other irrational numbers like √2, we think those are normal. Computers suggest that they're normal numbers by looking at the decimals. Okay? But we still can't find not even a single example of a normal number which hasn't been artificially constructed. However, we know that most numbers are normal. That's the weird thing.
What?
So yeah, you heard right. So there's an open problem. Find an example of a normal number. I'll put in brackets here. That's not artificially constructed. Because we could artificially construct it. Because we could find an artificially constructed number. Let me give you an example of such a number. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and so on. Okay? Basically all the digits. All the natural numbers strung together as decimals. This is an artificially constructed number which has been proven to be normal. Okay? But where does that ever occur? I mean, we just came up with it. It works. But it's nothing interesting. Okay? We would like to know if other numbers are normal. Okay? So there's an example of a normal number, artificially constructed number. We can't prove whether any other numbers are normal. Okay? A little bit about the progress, because the progress here is pretty interesting. It was proved in 1909, I believe it was, that most numbers are normal in the following sense. Whoa. The board is, yeah, I guess I'm not going to try pulling it too far down because it might fall out. Okay, so in 1919, sorry, what did I say? 1909, there we go. 1909, a guy named Borel proved that in the Lebesgue measure sense, I'm not even going to write that, maybe I should write that word if you're interested. There's how you spell it, Lebesgue measure, okay? In the Lebesgue measure sense, okay? Probably don't know what Lebesgue measure is, but you can look it up if you want to. So Borel proved that in the Lebesgue measure sense, 100% of numbers, real numbers, are normal. Okay? So the numbers for which this property of decimal regularity fails is very tiny. Okay? Of course, all the rational numbers and integers and stuff like that are in there. But it turns out that most numbers are irrational. And most of those irrational numbers are normal. So this is actually kind of weird. We know that most numbers are normal, but we can't even prove that a single one is, that a single example is. Okay? So there's a few more things I prepared for today, but it looks like I'm going to have to be, looks like we're going to have to get out of here because there's another class coming in. So we're going to cut it short for today. Maybe later in the semester there'll be another seminar on more open problems. Okay? Because we didn't get to some of the most interesting stuff that I wanted to get to, despite skipping stuff along the way. So thanks for coming.